So far we've been doing a lot of calculations with gases, and we need to stop for a minute and discuss some of the assumptions that we're making based on kinetic molecular theory. So we are considering or looking at the gases as being extremely far apart. So the molecules within a gas are floating around, but there's a lot of space in between them. And so we've been looking at the molecules as basically just being points in the container, and we've assumed that they have mass, but we really have been ignoring their volume. So we haven't been considering the volume of the molecules. Okay. The second assumption we've been making is that the collisions that the molecules make when they do bump into each other is that they're perfectly elastic. So they collide and then move on. There's no energy changes. There's no attraction. There's none of those types of things. Okay. The third assumption we're making is that gas molecules exert neither attractive or repulsive forces on each other. So when they do bump into each other, they're not attractive, or they're not basically repulsed by one another. The last assumption we're making, or have been making, is that the average kinetic energy of the molecules is directly proportional to the temperature of the gas in Kelvin. So basically, any two gases at the same temperature, they're going to have the same average kinetic energy. So we've been making these assumptions throughout our calculations so far. We've been saying that the gases therefore behaving as ideal gases, and not considering any of the other potential volumes or collision types or attractive forces that may actually come into effect in reality. Okay, so the compressibility of gases, we've been saying that there's a lot of space in between the particles of the gases so that the gases are able to be compressed. So I think that that's, if we apply a force or if we apply pressure, the particles will come into closer proximity to one another because the spacing is so great. In Boyle's law, we've been saying that P is proportional to the collision rate with the wall. So basically, in this situation, if you decrease the volume of your container, so if I have, let's say I have a gas container with like 2 particles in it, or a gas-filled container with 2 particles of gas, and I take that container and basically make it much smaller, okay, the decrease in that volume is going to increase the density of my particles, so they're going to bump into the wall more frequently, and subsequently you're going to have a larger pressure in that container. With Charles's law, we're saying that pressure is going to be proportional to the collision rate with the wall. So basically, if we take one container that has, once again, those 2 particles, and we take that same container, same size, and increase the temperature, basically the particles are going to be moving so much faster that they are going to bump into the wall more frequently and with more force, and so you're subsequently going to have a higher pressure as you increase your temperature. With Avogadro's law, we've been speaking or discussing the addition of gas particles to a container. So if I have a container with, once again, just 2 particles of gas, okay, and I take that same container and basically now add 2 extra particles of gas. By having more particles, I've increased the density of the gas in the container, and subsequently I've increased the number of collisions with the walls of the container, so I've subsequently increased the pressure in that container. And then Dalton's law of partial pressures, we've been saying that because of the fact that the particles themselves don't attract or repel one another, the pressure exerted by one type of gas in a container is not going to be affected by a different type of gas in that same container. So there's a lot of assumptions that we've been making. You guys want to make sure that you can go through the thought processes and relate the changes in a container based on Avogadro's law, Boyle's law, Charles' law, etc. So basically, if you've added more gas, how's that going to affect your pressure? Or if you change the temperature, how does it affect your pressure? Okay, these are things you want to think through and kind of process and make sure that you're comfortable with. Now, as I said, these are the assumptions. This is the thought process we're using when we're calculating for ideal gases. So that's the assumption we're making 99% of the times in our calculations. And we'll discuss situations that are outside of those ideas in the next video.